This class. Last class, little bit I have explained how to design the control unit. You have seen for your control unit, it has some input signals. It also generates some output signals to control the operations of the instructions. Now, you have considered the 7 macro instructions. For each macro instructions, to execute, we need some micro operations. Okay, and for all the macro instructions, some operations are the fixed. For example, that is a fetch operations. So fetch operations, here we have considered the C0, C1, C2 and C3. That means 4 control signals, that means 4 operations we consider. And of course, I'll request you that don't feel that it is the exact operations what is required for a particular processor. It is these are only our assumption. And we have considered a hypothetical machine, and if we consider, suppose these are the consider, or you can assume this type of the operations, then based on these operations we are trying to design our control unit, different type of the control units. So first, it is very important, whatever your type of the control unit, but you have to know the what are the micro operations. If you can't define the micro operations, then you cannot define the what are the control signals will be required to activate all the micro operations. So you should have the basic knowledge, whatever you have studied the 8085 instruction set, and whatever the other instruction set you have studied. Bivas has given some lecture, has given some some information to you that how it will be executed. Okay, so basic, you can say that basic concept of execution of an instruction that you should have. Otherwise, you cannot define the micro operations. That micro operations that maybe you can do with the help of the 4, or it may be the 5, it may be the 6. It doesn't create any problem, but haphazardly you cannot write. Okay, always you should know the what are the steps. First step is that fetch operation, next is decode, then it will do the execution, depends on the instruction. So load operation, what is the load operation? That concept you should know. What is the store operation? That you have to know. What is the add? What is the and? What is the jump? What is the jump on different condition? That basic concept you have to know. Otherwise, your assumption of your micro operation will be wrong. So first step is that you you study the different instructions available in different processors, and what is the way to execute that instruction with the help of processor. That you have, that basic knowledge you should have. Otherwise, you cannot define the micro operations. So if you can define the micro operations, so easily you can define the micro, you can say the micro signals. That means micro instruction, what can be done, what can be, you can say that which control signal can activate which micro operations. Okay, so what are the control signals will be required for executing different micro operations, easily you can define. So your difficulties may be happen when you find out what are the micro operations will be required for a macro instructions. So for 7 macro instructions, you have seen these type of the control signals will be required. For load, what are the instructions will be required? C0, C1, C2, C3, again C4, C1, C5. For your store, what will be required? C0, C1, C2, C3, C4, C6, C7. For your add will be required C0, C1, C2, C3, C4, C1, C8. And for your AND instruction, logical AND operation, you need C0, C1, C2, C3, C4, C1, C9. For your jump instruction, you need C0, C1, C2, C3, C10. And for your jump Z instruction will be required C0, C1, C2, C3 and C10. Again, both are the same, but depends on the Z instruction. Whenever you design the circuit, on that moment Z flag will be involved. Okay, and for your last instruction, that is the complement of accumulator, that is the C0, C1, C2, C3 and C11. So you can understand that for all the instruction, fetch operations, that is the same. And what are the corresponding micro operations will be required, that is C0, C1, C2, C3, all are common. Okay, these are the basic concept of your designing the design about your control unit. Okay, and for delay element method, you have seen after defining all the control signal, you just place some delay elements. So it is a difficulty of your delay element method depends on the number of your micro operations. You need the number of your delay element. N number of micro operations will be required, so n number of delay elements will be required. At the same time, you have a problem for your clock synchronization. Clock synchronization problem you will study when you study the distributed computing. Distributed computing, there you will study the clock drifting and how the clock can be fast and slow and how you can synchronize this type of clocks. Different methodologies are there to synchronize the clocks. Because of that, physically it is very difficult to get the same delay from the delay elements. Okay, so this is the difficulty for your delay element. Now this limitation, if we have, then we are trying to generate another way, that is basically with the help of some sequential logic and with the help of some combinational logic. Here we don't want to use any delay element. Without using delay element, we want to control with the help of some sequential logic and also some combinational circuit. That circuit doesn't require any delay. Okay, delay element, not delay hardware will be required. So now, whatever the operations, suppose here we have considered the 7 macro operation. After considering 7 macro operations, we have the most probably 11 or 10 C0 to how many C0 to C11. That means we have the 12 number of micro operations we have. Now for this micro operations, we divide into some phases. Okay, see that some operations are very common. That is the sometimes you can consider, suppose memory read operation, memory write operation. Actually fetch operation, fetch always we use the term that is to read the opcode from your memory. Actually this is used for your fetch. Fetch is also a memory read operation. So memory processor can read to read the opcode as well as sometimes to read the address, sometimes to read the data. So many times for many purposes processor can read the memory. So memory read is common, and memory write operation also we can do for many times. So it is not like that only load operation will do the read operation. Many macro instructions, if you can see, there is also required some memory read operation as well as some memory write operations. All these operation we can write in these phases. Suppose phase 1, phase 2, phase 3, phase 4, phase 5, phase 6. These 6 phases we can consider. Phase 1 and phase 2 and phase 3. These 3 phases here I have considered for your fetch operation. Total fetch operation. Fetch operation means that address register content will go to the program counter. From that memory location, the data will read and will be stored into the instruction register, and also program counter will be incremented and it will interpret the meaning. Control unit, of course, one of the vital operation is that to interpret the meaning. So first operation is the fetch operation, and that we can do with the help of 3 phases: phase 1, phase 2, phase 3, and other operations, that is phase 4, phase 5, phase 6. To do the operation depends on your instruction. Okay, now suppose This is already I have explained how you can design. This is a modulo 6 counter. So modulo 6 counter means that you can have the value 000 to 111. But previous class, that is your advanced, sorry, your digital electronics class, you have seen that it can go to the 8, but we can control these lines in such a way that we can have from 000 to 101. That means we can generate the phase 1, sorry, that means 6, 0 to 5, that means 6 output signals. Okay, but decoder we can use here 1 to 8 decoder. Last two lines we do not want to use because we do not want to need, and most of the time these input lines never, these input patterns we never get. Sometimes you have some glitch, you have some any other problem, there may be it comes to 111 or 1110, it may come, and you know that how to solve this type of the problem, and that you have studied in your digital electronics class, how to remove this type of the problem. But whatever it is cases, we consider here the 6 phases, so we do not need phase 7 and phase 8. If we need, of course we will use the phase 7 and phase 8. Okay, so depends on you how many phases you want to consider, that depends on you. So if it is required more on that moment, you should use that type of the modulo counter. Okay, now here modulo 6, with the help of modulo 6 counter, we can generate the 6 phases. So it is you can call as a modulo 6 sequence counter. Now this modulo 6 counter you can utilize to design your combinational circuit. Now see that what has happened here, modulo 6 counter, just a minute better. Now here you see the diagram, here modulo 6 counter is here. So this you understand that how it can generate the different phase signals. Now check that for the first signal, that is the phase 1. So phase 1, what is the phase 1? Phase 1 we have considered that is a first operation, micro operation of your phase operation, fetch operation. What is the fetch operation? That is address register content should go the program counter. Now see that whatever the instruction that doesn't depends on you. Okay, so it for each and every instruction this operation is same. Okay, this operation you can say that for all the macro instructions you have these operations, so it doesn't depend on the instruction. So for that reason what is happen, when it will generate the C0 at the time of phase 1, it doesn't depends on the other. See that directly it generates the C0, it doesn't depend on any other instruction. Now go for the C1. So C1 is that it after having the data, having the address, from that address that data or opcode, or you can see that any address also it can stored into the data register. Okay, so whatever the content of that memory, sometimes it may be the opcode, sometimes it may be the operand, sometimes it may be the address of operand. Okay, but we do not check of that. Whenever if we have the fetch operation, of course it should be the data of your data should be your opcode. Now check that again. I go to the first, see that here this is for the fetch operation, it of course it is a opcode. Okay, for fetch operation, fetch the opcode means that it should be the memory should have the opcode here. Okay, so these operations you have where now phase 2. Okay, but here you can see that or, okay, to generate the C1. Now again you check your macro instructions, the C, and also the micro operations, that is a C1 is also here, and also you have here, also you have here. Check that. So for these cases also it will generate the phase 1. So for that reason, for your phase 2, phase 2 operations. So it automatically comes for your fetch operation. At the same time, when exert operations will be required, that means for the load, here you can see the add, here you can see the add. So for this thing, again you have seen that these operations are doing in the here. Okay, C1. So C1 depends on the phase 2 and also depends on the phase 5. Phase 5 means that you can say, again I go to that, sorry, suppose that this you can say that phase 1, this is the phase 2, this is the phase 3, and this is the phase 4, and this is the phase 5, this is the phase 6. Okay, so see that phase 2 and phase 5, for both the cases you have the C1 signal. Clear to you? So for that reason, in your combinational circuit, where you generate all the control signals, there combine phase 2 and phase 5 with the load and and. For these instructions, it will generate the C1. So when C1 will be 1 when phase 2 coming, or phase 5, but depends on the instruction. What are the instruction? Load, add, and and. In this way, you can find out the logic for your control signal, that is C1. First, you tell me, is it clear or not?
Ma'am, could you repeat this part, ma'am? I didn't understand.
See that whatever the operations you have, what are the operations? These are the operations, better? Clear? For the fetch operation, what are the operation you do? This, and this. Clear? And also this. These are for your fetch operation. And corresponding signals are C0, C1, C2, and C3. Clear? So for the first
Yes, ma'am.
operation is that program counter content should go to the address register. Okay, so it doesn't depends on any instruction. So for that reason, phi 1 directly it will generate the C0. See that this line is independent of the other signals. Here it is not combined with any other signal. Directly it goes to the C0. Whenever processor starts to execution, always first operation is the opcode fetching operation. So for opcode fetch operation, what will be happen? First part is that content of address register should go to the program counter. Sorry, program counter register should go to the address register. Okay, in that way we can define. Program counter content goes to the address register, and from that address register the opcode will be read and transferred to the data register. These operations are the fixed. Okay, so for that reason, for the first case, for phi 1 and first operation is that C0, without any dependencies it will generate the C0. And for the phi 2, second phase, what is happen? The content of that memory will be stored into the data register. Okay, these operations, this C1 operation, you can observe at the time of the phase 2. At the same time, you will observe at the time of the phase 5. Why it is the phase 5? Again, you have to understand how the macro instructions are executed. See that here, for the load, you have here, you also have here, you also have here. So I have divided, I have used some phases: phase 1, phase 2, phase 3, phase 4, phase 5, phase 6. So in the phase 5 also, the processor or control unit should generate the C1 control signal. So for that reason, when you design the combinational circuit, you should keep it in mind. So how it is designed? Check that. First is depends on also phase 5. Okay, this is the AND gate. So AND gate, of course, if it is the phase 5 is 1, it is not sufficient condition. At the same time, it should satisfy this value also. Both are 1, then will be 1. This is the AND logic. So here it will be 1. If you have from this part, or from this part, this is the OR gate is there. So any one is 1, on that one it will be 1. Clear? So you have seen C1 signals will be generated at the time of the phase 5 for the instruction, that is load, add, and AND. So on that moment, it will generate the 1, and from 1, here it will have the C1 will be 1. Now you understood better? Little bit
Yes,
difficult,
ma'am.
but
Yes,
not
ma'am.
very difficult. If you can understand, please again. Now go to the next, then I hope you can understand this part also. Now go for the phase 3. Okay, for the phase 3, what are the operation phase 3? Phase 3 operation is that the content of that data register, will move to the instruction register. You know that opcode always stored into the instruction register, and program counter value will be incremented by 1 or k, depends on the instruction. So these two operations we define with the help of the control signal, that is C0, C1, this is the C2, and this is the C3. And for all the instruction, these operations should be done. Okay, so for that reason, directly it can gives the signal C2 and C3. It doesn't depend. We never use any gate here. So that means that it doesn't depend of any instruction. This is common for all the instruction. Clear? Now I have not designed here for the 5-4. Okay, that phase 4 you can do. So what is the phase 4? Check that. Where is the phase 4 better? Phase 4. So what is the phase 4? Phase 4 is that address operand, transfer operand address to the address register. Now go to the instruction. What you have seen? This is the C4 beta. Okay. So what are the instructions that follow this operation? Load, store, add, and. Okay. So this C4 operation is done by the load, store, and add and you don't have here. Okay, so for that reason, what is happen, how you can do? So for phase 4 operation, if you want to generate the C4 operation, on that moment, what you will do? Here, from here already you have the this 3, many to 1 you have to do, and just combine this. Again, you can do the 1 OR gate, and this operation you want to do at the time of the phase 4. So that should be the AND gate. From AND gate, you can generate the C4 operation. So logic is very simple. You just observe the phase and what is the operation and what are the micro operations will be required. And on that moment, based on that logic, you draw the combinational logic. Whatever your logic you will find out, easily you can convert with the help of some combinational circuit. Okay. Now here, suppose last operations, these are all the execution operation. You can see the operations for your load, stored, and other operation. See that this is the C5 operation. Here it is a C6 and C7 operation. For the execution phase, I am telling. Okay, and here you have the C8 operation. Then C9. This is the C10. Here is also C10. There is a C11. So all these are you can implement with the help of the phase 6. Okay, with the help of your phase 6 you can do. So now, if you have in this way, so you can generate the signals from C5 to C10, C11. Okay. Now here I have drawn the figure for C10 and C11. You can do for other signals. So check that for the C10 when you have the for jump instruction, you have jump Z instruction. Okay, and C11 you have for your complement operation. Okay, this here also C10. Here also you have the C10. Here is the unconditional jump. It is a conditional jump. Based on the value of your jet flag, you can go to the, you can generate the C10 signal. Now see that here the phase 6. Clear? Phase 6 is for exact execution, depends on your instruction. So what is happened? Come to here, then it is the AND gate. This AND gate, that means it depends on the OR input. Now see that this is a jump instruction. So jump instruction directly it comes to here. So any one is 1, it will be 1. So it doesn't depend on the jump Z instruction. It depends on the jump instruction. You can say that. So for this line, So for this line, it comes from the jump operation. So jump is 1, on that moment it is 1, and it will phase 6, it is 1, both are 1, on that moment it will generate the C10. Okay, now for the jump Z, okay, jump Z signal depends on the Z flag. So for that reason it comes from the Z. Okay, it comes from the Z flag, and it will combine, because both should be true. That means we have to place here the AND gate. If both are 1, on that moment output will be 1, and it is a many to 1 is required, because C10 is for your jump as well as jump Z. That's why here you have placed here the OR gate, and from OR, and it is in the phase 6 operation. On that moment it will generate the C10. So C10 can generate when you have the signal, you have the operation that is a jump or jump Z, and you have to combine for jump Z operation on that moment, that is a Z flag. If you have to combine with the Z flag, then you can generate the C10 during the time of the jump Z. Now last is that C11, that is a complement operation. So again it is a phase 6, and also it is a complement instruction should be there. So you can generate the C11. Clear? So this part already you have seen that how to generate the different output signal from the instruction decoder circuit, and it is your to select the phases. What are the phases? You can normally say that one is that phase, decode, and execution. Depends on the instruction. It will be that can be generated some control signal for exact execution of the instruction. Okay, so you can come. I hope you can complete the instruction for you can design for your control signals, that is C5 to C9. I hope you can do that. After that, you understand that better. It is not complicated circuit, but it is very easy. And another way you can understand, I have written here the Boolean expression. This is the Boolean expression. Okay, so C1 when it will be generated at the time of phase 2, and it is at the time of phase 5, but that depends on the signal. In this way, you can write the Boolean expression, then you can draw the circuit from here to here or here to here. That depends on you. Okay, so if you find out the expression easily, you can find out the design. See that C0 at the moment of phi 1, C1 you can have the value phi 2 and phi 5, and you have the C2 that is a phi 3, C3 that is a phi 3, C4 is that already I have done for the C4, that is phi 4. At the same time, for this instruction you cannot write for jump and complement instruction. Okay, that for that part you cannot write. Now C5, that is a phi 6. Obviously, you have seen that that is C5, C6, C7, C8, C9, C10. All are you can doing at the time of the phase 6. So phase 6, and you should have that instruction. Then you can generate corresponding control signal. Okay, so it is very easy. Just you use the AND gate, nothing else. Only use the AND gate. So phi 6 and that signal. So obviously you'll implement with the help of logical AND gate. And for your C10, because you have the jump, you have the jump Z. Suppose if I include another instruction, suppose jump E, that means even parity. So you, on that moment, here I have considered the Z flag. On that moment, you have to consider the parity flag. Okay, suppose if again I can write JMP, not the JMP, yes, JMP C, suppose. Okay, for carry. So on that moment, you have to consider the carry. On that moment, here you have to include all the instruction. Okay, you have to include. So it depends on your consideration. What are the instruction you want to use to design your control unit? Based on that, you can write this control signal and find out the phases, at which phase what operations can be performed by the processor. Based on that, you write the logic, and you can design the combinational logic. This logic is very, very simple, but step by step you have to do. Beta, do you have any question? It is an online class. What can I do, beta? I cannot use blackboard and chalk.
Ma'am, kind of got it, ma'am. If you could, like, after we read through the notes, probably it will be easier to understand, ma'am.
After mid same. Now you
After
have a
no,
problem,
after
no?
we read the no, after we read the notes, ma'am. After we read the notes, like the notes
Acha,
that you
okay,
sent.
okay, okay. Just you today already I sent to your seer this note.
Yes, ma'am. Yes,
Okay,
ma'am.
you
Yes, ma'am. We
collect
got it,
it
ma'am.
again. You read. Okay,
Yes, ma'am.
a step by step you have to do. First step is that you should consider some instruction arbitrary. Okay, you will check with different instruction. Here I have considered the load and store. You consider different type of the move instruction. Move instruction, if you consider in this way, that is a if sorry, if you use the move a comma b, so for that you will have the very simple control signals will be required. But if you consider suppose move m comma a, on that moment you need more number of control signals. So with the help of the different type of the instruction, you try to prepare the different types of the control signal. This is the first step. Second step is that delay element method is just you control flow, you just draw. Otherwise it is it doesn't have anything in between two activating signal. You place the delay element, nothing else. So only you for the delay element method only you understand the flow of the control signals, how to activate all the signals, that is all. But for your sequential counter method, you have to define the your operations into different phases. That depends on you. You can use, here I have used the phase 1, phase 2, phase 3 for your 3 operations. Here you can use phase 1 and phase 2, or you can use the phase 1, phase 2, phase 3, phase 4. That depends on you. And after that, what are the other operations for execution, the exact operations? Load, what is the loading operation? That means from memory to processor, store operation from processor to memory. So depends on the instruction, it has some other operations that you can distribute it over some phases. Here I have written the phase 4, phase 5, phase 6, but if you want you can use more than that. That means you can use the 5, 6, 7, 8 in that way. So after having that, you select the your sequence counter, that is modulo 6, modulo 8 or modulo 10. That depends on the number of phases you have. After having these phases, you just combine all the signal and all the phases, and here you one by one you observe the operation, and here you can find out the logic to generate one control signal. So in this way if you do, I hope you will not have any problem. So today I don't want to continue. I can start microprogram control, a little bit tough. Okay, this is the software approach. Next class I will explain. Okay, so first
Ma'am, will this PDF be part of our CA2 syllabus, ma'am? Like this specific topic?
yeah, that is the I'm thinking of that microprogram control unit. I want to complete before your mid-sem. Okay, if you feel problem, then I will eliminate for this time.
Okay,
Okay.
ma'am. Okay, ma'am.
And but if you know the control design part 1, then it will be very easy for your second part better. If you have any problem in your control design first part, you will have the problem for the control design part 2. Okay, so you should understand what is the macro operation. Macro means nothing but whatever the instructions you have used in your assembly programming. So that is a load, add, that type of instruction. One macro instruction, we can divide a set of operations. That set of operations we can define as a micro instructions. Micro operations, micro instructions, nothing else. Okay. And here we use the microprogram control design. We use some control memory, and with the help of the control word, we store the micro instructions. Next class, I will explain this class, this part. Okay. In your Wednesday, I will take your class. Wednesday,
Okay,
you
ma'am.
don't have any exam, na, from 1:30?
Ma'am, Wednesday we don't have any exams, ma'am.
Okay, so next class I will complete. If you face any problem, then I will discard from your syllabus at this
Okay, ma'am.
moment.
Okay, ma'am.
Clear?
Yes,
Okay,
ma'am.
better. So now I want to stop better.
Okay, ma'am. Thank you, ma'am.
Thank you, ma'am.
Okay.
Thank you, ma'am.
Okay, better. You can leave.